At 11 o'clock at night, a new sun opens above the Pacific, and it is not supposed to stay there. The sea stays dark, but the sky turns red, then white, then green, like the planet is trying on a wound. Streetlights on Hawaii blink, radios hiss, alarms wake up, and nobody on the beach can yet see the real disaster. The fire is already fading, but something invisible is beginning to circle Earth, and it will keep hunting long after the flash is gone. If you like true stories where the strangest part is also the most real, subscribe now and stay close. There are a lot of loud space stories online, but very few tell you what actually happened when human beings touched the sky with a bomb. And this one does not end when the explosion ends. To understand why this happened, you have to go back to the Cold War, when fear was not just in speeches or newspapers, but in science labs, missile bases, and control rooms. The United States and the Soviet Union are both building bigger bombs, longer-range rockets, and new machines that can rise above Earth, because each side is terrified the other side will get there first. Space is no longer just a dream by then, and it is no longer just a place for wonder either, because satellites are becoming useful for communication, spying, tracking, and proving power. So the sky above Earth is turning into a new frontier at the exact same time the most dangerous weapons on Earth are getting stronger, which is a terrible mix. People often imagine the early space age as clean, hopeful, and full of brave explorers looking up at the stars with pure excitement. That feeling was real, but it sat next to another feeling that was just as real, and that feeling was panic. If the next war happens with rockets and nuclear weapons, then space may become part of the battlefield, and military planners want answers before a real enemy gives them the lesson first. That fear pushes nations to ask questions that sound insane now, like what a nuclear explosion would do not just over a city or ocean, but high above the planet itself. There is another piece to this story, and it starts with a discovery that surprises scientists only a few years earlier. In 1958, American missions helped reveal the Van Allen radiation belts, giant regions of trapped charged particles held in place by Earth's magnetic field. That may sound abstract, but the simple version is easy to picture. Earth is wrapped in invisible zones of dangerous energy, and anything flying through them can get hurt. Suddenly, space stops looking empty, because now it has weather, danger, and places that can slowly damage machines even when nothing seems to be there. That discovery creates both wonder and worry, because it means Earth is sitting inside a magnetic system much more active than people had understood. Scientists know that a nuclear explosion throws out huge amounts of energetic particles, including fast-moving electrons that carry electric charge. So a dark question appears. If a bomb goes off high enough, could Earth's own magnetic field trap some of that energy and turn one moment of violence into something that lasts? Nobody knows for sure, and during the Cold War, not knowing is often treated as a reason to test something instead of avoiding it. That is how the United States arrives at a series of high-altitude nuclear tests called Operation Fishbowl, part of a much larger testing effort named Operation Dominic. The test area is Johnston Atoll in the Pacific, a small, remote base southwest of Hawaii, chosen because it is far from crowded land and useful for military launches. From there, rockets can carry warheads high into the upper atmosphere and beyond, while aircraft, ships, cameras, and instruments spread out to collect data across a huge area. It is a grand experiment built out of military fear, scientific curiosity, and the dangerous confidence of an era that keeps believing it can control anything if it measures enough details. The most famous shot in that series is the one history remembers as Starfish Prime, but even that event almost never happens the way people planned. An earlier launch on June 20, 1962, fails when the Thor rocket begins to break apart, and officers have to destroy it before it can become an even larger disaster. Radioactive material from that failed attempt falls back toward Johnston Atoll, contaminating parts of the island and warning everyone that this project is already risky before the main test even begins. Still, the mission is reset instead of canceled, because the pressure to learn is stronger than the warning coming from the failure itself. On July 9, 1962, the next attempt goes forward. A Thor missile lifts off carrying a thermonuclear warhead with a yield of about 1.4 megatons, around 100 times the power of the Hiroshima bomb. It climbs to about 250 miles above Earth, or roughly 400 kilometers, which is high enough that most people watching below cannot use normal, everyday ideas to guess what the blast will look like. When it detonates, the explosion happens in a place too thin for a normal mushroom cloud, too strange for a normal shockwave, and too connected to Earth's magnetic shield to stay simple. This is the first big gap between expectation and reality. Many people imagine the main result will be a bright flash, maybe some useful military data, maybe a short-lived disturbance that fades as fast as fireworks over the ocean. Even some experts do not expect the long damage to be so severe because they assume space will swallow most of the event and spread the rest so thin that it will not matter much. Instead, the blast does something almost poetic and deeply dangerous at the same time, because it turns the sky itself into a display that is beautiful enough to distract people from what is really starting. Witnesses across Hawaii see an impossible scene. The darkness above the Pacific suddenly glows with red, pink, and green light, like a new aurora has appeared in the wrong place at the wrong time and for the wrong reason. Some people describe it as a false dawn, because the brightness feels like morning arriving from a direction where morning does not belong. Others remember arcs, streaks, and glowing shapes stretching across the sky, hanging there long enough to feel less like an explosion and more like the planet has opened a strange, luminous wound. If you had been standing in Hawaii that night, would you have thought you were watching a science test, the end of the world, or something from another planet? Tell me in the comments, and if real events like this are exactly why you come to YouTube, hit like and subscribe. Because the glowing sky is only the part people can see. On the ground, the first surprises arrive fast. In Hawaii, streetlights fail, radio links act strangely, alarms trigger, and electrical systems begin behaving in ways that do not match the normal picture of a distant blast. One common account says around 300 streetlights go out on Oahu, hundreds of miles from the detonation point, which is a small effect compared with what later generations fear from EMP, but huge compared with what many people expected in 1962. The test has produced a strong electromagnetic pulse, or EMP, a burst of energy that can create sudden electrical trouble far below the explosion itself. That matters because a bomb in space is not like a bomb near the ground. Near the surface, much of the energy goes into blast pressure, heat, and destruction in the local area, and people can picture walls falling, fire spreading, and windows breaking. But high above Earth, there is almost no air, so the energy follows stranger paths and interacts with the magnetic field, the ionosphere, and huge regions of space. The explosion throws out fast charged particles, and those particles do not simply drift away into emptiness, because Earth grabs many of them with its magnetic field and forces them into new paths. This is where the event stops being a dramatic flash and becomes a scientific shock. Later researchers explain that the detonation releases an enormous cloud of energetic electrons, and Earth's magnetic field captures many of them in near orbit. In simple terms, the planet catches part of the explosion and bends it into a belt of trapped radiation, turning one short violent event into a long invisible hazard. That means the real aftermath is no longer one blast over the Pacific, but a new man-made environment wrapped around Earth, waiting for satellites to pass through it again and again. Before Starfish Prime, scientists know that the natural Van Allen belts exist, but they do not fully expect a human weapon to create a major artificial belt so suddenly and so effectively. Some believe the effects may be noticeable but manageable, may be useful for measurement, may be dramatic but limited. What actually happens is far worse for machines in orbit, because the artificial belt raises radiation levels in ways that begin damaging satellites that were never built for that kind of punishment. It is as if the United States has accidentally added a new trap to near-Earth space, and its own technology becomes some of the first prey. One of the clearest examples is Telstar 1, the famous communications satellite launched just one day after Starfish Prime. Telstar is meant to help carry television signals, telephone calls, and other communications across huge distances, a symbol of a connected future rising into orbit. Instead, it enters a space environment poisoned by the recent test, and later accounts say it receives radiation levels far beyond what engineers expected, damaging its electronics until it fails. A NASA presentation even describes the radiation dose as about 100 times higher than expected, which tells you how badly the environment has changed. Telstar is not the only victim. Ariel 1, the first British satellite, is also damaged, and other spacecraft begin showing problems as the hidden belt keeps doing its work. Different historical sources give slightly different totals, which is normal when failures happen over time, and not all damage looks the same at first. But many accounts say at least 1/3 of the satellites then in orbit are affected. That number sounds small today until you remember how few satellites existed in 1962, which means one experiment harms a huge share of the entire early space age. Here is why that difference between belief and reality matters so much. A normal explosion ends, and then people count what was broken nearby, clean up what they can, and slowly move on. Starfish Prime does not work that way because its most important wreckage is invisible and stays overhead, circling the planet where machines keep crossing it later. The bomb becomes a long-lasting bad neighborhood in space, and every orbit through it becomes another chance for failure. Did you expect the strangest part of this story to be not the flash, but the leftover danger hanging over Earth after the fire was gone? If that surprises you, type invisible in the comments and subscribe for more stories where the hidden part matters most, because the next layer of this story reaches even farther. The visual display from Starfish Prime is so intense that many witnesses never forget it. Some describe the sky as blood red in places, or as bands of shifting color that seem to hang and move with a life of their own. Observers on Maui and elsewhere watch bright forms spread and fade for minutes, not seconds, which makes the whole event feel less like a weapon test and more like a new kind of unnatural weather. The beauty is real, and that beauty is part of what makes the memory disturbing, because people are seeing something magnificent at the exact moment it is creating damage they cannot sense. That contrast between beauty and danger tells you a lot about how humans misunderstand disasters. We trust our eyes, so the glowing sky becomes the memory that lasts in many public stories. But the real violence is taking place inside circuits, across magnetic field lines, and inside bands of radiation wrapping around the planet where almost nobody can look directly. Starfish Prime teaches a brutal lesson. The most important effects in modern technology disasters are often the ones that do not look dramatic at all. It also shakes confidence inside the scientific world. The physicist James Van Allen, whose work is tied closely to understanding Earth's radiation belts, later admits he did not expect the very large trapped radiation effects from the Starfish event. That matters because it shows this was not just a public misunderstanding or media exaggeration. Even experts working near the problem are still learning how powerful the interaction between a space explosion and Earth's magnetic system can become. And that makes sense when you remember the limits of the era. In the early 1960s, computers are weak by modern standards, models are simple, and many of the most important plasma and magnetic effects are extremely hard to simulate. Scientists can measure pieces of the problem, guess at others, and build theory, but the full three-dimensional behavior of a huge nuclear event in near-Earth space remains incredibly hard to predict well. In plain terms, they do not fully know what the sky will do when the bomb goes off, and the only way they learn is by letting it happen. The Cold War also helps explain why such a dangerous uncertainty does not stop the program. American leaders are afraid the Soviet Union may discover strategic effects first, whether those effects involve missile defense, radar disruption, communications failure, or damage to satellites. Military planners want to know what a nuclear explosion high above Earth might do in war, even if the question itself sounds monstrous. So the test is driven not only by curiosity, but by the logic of fear, where the thought that an enemy might act first can make almost any experiment seem necessary. Public criticism exists, of course, and not just inside the United States. There are protests in places like London, strong objections in Tokyo and Moscow, and moral condemnation from people who see space testing as proof that the nuclear arms race has broken every sensible limit. To many ordinary observers, setting off a nuclear bomb in space sounds less like science and more like civilization losing its mind. But in that moment, the momentum of competition is stronger than the warning voices, and the launch still happens. Then, history brings the world even closer to catastrophe. Only a few months after Starfish Prime, the Cuban Missile Crisis pushes the United States and Soviet Union to the edge of nuclear war. For several terrifying days in October 1962, the world faces the possibility that fear, weapons, and bad judgment may combine into a civilization-ending exchange. That crisis changes political thinking, because leaders on both sides now feel, in a much more personal way, how close human beings may have come to disaster. This is where the story begins turning into policy, instead of only memory. In 1963, the United States, the Soviet Union, and the United Kingdom signed the Limited Nuclear Test Ban Treaty, which bans nuclear tests in the atmosphere, underwater, and in outer space. It does not end the arms race, and it still allows some underground testing, but it draws a line around some of the most dangerous environments that had been used for experimentation. Starfish Prime is not the only reason that treaty matters, but it helps show why letting nuclear weapons loose in the sky is not something any nation can safely manage. A few years later, the 1967 Outer Space Treaty builds on that lesson. Among other things, it says space should not become a place where weapons of mass destruction are stationed, because orbital space is too shared and too critical to poison with that kind of threat. That may sound obvious now, but it only sounds obvious because history has already shown what one high-altitude test can do, even during the early days of spaceflight. Starfish Prime helps teach the world that a nation does not really damage only itself or its enemy when it damages the space around Earth. If leaders today treated near-Earth space the way leaders did in 1962, how long do you think modern life would stay normal? Leave your guess below, and if you want more true science stories with stakes that reach all the way into daily life, subscribe right now, because this old event is still speaking to the present. Back in 1962, losing or damaging a third of the satellites in orbit is alarming, but the total number of satellites is still tiny by modern standards. Today, the number of spacecraft circling Earth is not measured in dozens, but in thousands, and many more are launched every year. That means the same kind of artificial radiation event now would not just damage a handful of early experimental machines, it could hit communications, navigation, weather monitoring, Earth imaging, financial timing systems, military networks, and the daily tools that millions of ordinary people use without even thinking about where the signal comes from. Think about how much of normal life quietly depends on satellites. Phone timing, map directions, weather prediction, ship navigation, aircraft systems, emergency coordination, television links, internet backhaul, farming data, and military warning networks all reach upward in some way. Most people feel like space is far away because they cannot touch it, but their lives are tied to it through clocks, screens, antennas, and services that would become unstable if the sky became hostile. In 1962, Starfish Prime is a shock mostly to scientists and governments, but in a modern repeat, the shock could spread straight into homes, roads, hospitals, ports, and markets. There is another reason the story feels more urgent now. Human beings live in orbit today for long periods, and more missions are planned for the future. An artificial radiation belt is not just bad for chips and solar panels, it can raise serious danger for the bodies of astronauts passing through the wrong region at the wrong time. So the old lesson has grown sharper. We are not only protecting hardware anymore, but protecting people moving through the very space we once treated like an empty testing ground. The event also matters because it teaches scientists more about natural threats from the sun. A giant solar storm is not the same thing as a nuclear blast, but both can load Earth's magnetic environment with extra energy and create serious trouble for electronics and power systems. The famous Carrington event of 1859, for example, sent auroras far from the poles and shocked telegraph operators even in a much simpler technological world. By studying Starfish Prime, researchers gain a rough and ugly laboratory example of what can happen when the space around Earth becomes suddenly more dangerous. That does not mean scientists are helpless now. Modern computing lets researchers model parts of the Starfish event in ways people in 1962 simply could not. Decades after the test, released data and better simulations help teams at major laboratories reconstruct the magnetic disturbances, the ionized regions, and the slower pulse effects that move through Earth's environment. In other words, the world spends years trying to understand, with advanced tools, the thing it first created with far less understanding. Some of those reconstructions show just how huge the disturbance really was. A single simulation can cover an ionized patch of the upper atmosphere thousands of miles across, a scale so large it stretches beyond normal human intuition. Researchers explain that even with powerful supercomputers, it can take days to run detailed models of the event, because the explosion is interacting not with empty space, but with a vast, living magnetic system. That tells you something important and humbling. Starfish Prime was not a small local event that happened to be high up. It was a planetary-scale disturbance tied into Earth itself. Scientists also learn more about the EMP from later analysis. Instead of one simple electrical snap, the pulse has layers and phases, including slower magnetic effects that can matter across wide regions. That is why the lights in Hawaii and the strange electrical behavior on the ground matter so much historically. They show that a high-altitude nuclear event does not need to touch a city directly to start affecting systems below through long-range electrical and magnetic pathways. One of the strangest details in the whole story is how some of the most valuable data stays hidden for decades. Important measurements and recordings from the test remain classified or buried in archives, which means later generations know the outline of the story long before they fully understand its inner physics. At one point, old magnetic tapes tied to starfish data sit stored away in a garage, which sounds almost unbelievable for evidence from one of the most astonishing experiments of the Cold War. It is as if history itself knows the event is too strange to fit neatly into a filing cabinet. That long delay in understanding creates a second kind of aftermath. The first aftermath is physical, with radiation belts, satellite damage, and electrical trouble. The second aftermath is intellectual, because scientists keep returning to the event decade after decade, asking what exactly happened, how large the effects were, and what the world should learn before a new crisis creates a similar danger again. Starfish Prime does not stay trapped in 1962. It keeps reaching forward, forcing each generation to rethink what power means in a connected technological age. If a hidden belt of radiation could linger for years after one test, what do you think is the biggest modern weakness a similar event would expose first? Drop your answer in the comments, and if these real mysteries make space feel more alive and more dangerous, subscribe before we reach the final turn. Because the most personal part of this story is still ahead. The personal part is this: space is no longer somewhere else. When people in 1962 look up and see the artificial aurora, they are seeing a distant event that still feels somewhat separate from daily life, because only a few systems then depend deeply on orbit. Today, the same sky is stitched directly into our routines through location data, communications, forecasting, transportation, security timing, and the quiet electrical order that keeps modern society synchronized. That means the lesson of Starfish Prime now belongs not only to soldiers and scientists, but to drivers, patients, pilots, farmers, traders, rescue workers, and families who have never once thought about the Van Allen belts. There is also a moral lesson hiding under the science. The test shows how easily human beings can mistake a new environment for an empty target, especially when political pressure tells them they need fast answers. Near-Earth space looked open and silent, so leaders treated it like a blank range where a bomb could be fired and studied. But the environment was never blank, and Starfish Prime proved that brutally, because the planet itself took part in the event and spread its consequences through shared space. That idea should matter to anyone thinking about the future. As more nations and companies move into orbit, the temptation to treat space as a simple extension of earthly competition will only grow. Yet Starfish Prime reminds us that some arenas punish arrogance in delayed ways, where the damage does not arrive as one obvious blow, but as a poisoned system that keeps hurting everything passing through it. It is a warning that technology does not free us from consequences. Sometimes it only hides those consequences until they have had time to spread. In a strange way, the event also reveals something almost tragic about human curiosity. Curiosity helped discover the natural radiation belts, helped build the rockets, helped gather measurements, and helped later scientists untangle what happened. But curiosity mixed with military fear also helped put a bomb into a place where the wrong answer could wrap around the whole planet. So Starfish Prime stands as both a monument to human intelligence and a reminder that intelligence alone does not make a choice wise. That is why the story still feels alive now. It is not just about an old weapon test from a vanished phase of the Cold War. It is about how fast human power can outrun human caution, how beautiful danger can look at a distance, and how invisible systems can hold the fate of very visible lives. Those are not old themes at all. They belong to every age that builds tools faster than it builds humility. When people remember Starfish Prime only as the time the United States exploded a nuclear bomb in space, they are remembering the shortest part of the story. The detonation itself lasts a moment, the glow lasts minutes, and the public shock lasts days. The deeper event is the one that keeps circling after the fireball is gone, turning Earth's own magnetic field into a keeper of damage and a messenger carrying consequences through orbit long after the cheering, fear, and headlines fade. That is what makes the aftermath stranger than almost anyone expected. Even the numbers carry that strangeness. A warhead of about 1.4 megatons explodes roughly 400 kilometers above Earth, yet the damage reaches streetlights in Hawaii and satellites moving far beyond the line of sight of any person on a beach. An event that looks over in minutes keeps harming machines for months and leaves artificial radiation effects studied years later. Those are the kind of numbers that force your brain to slow down, because ordinary human instincts are not built to understand consequences spread across both altitude and time. And maybe that is the deepest mystery of all. We often fear the loud end of a disaster, the instant of impact, the visible break, the dramatic image that can fit inside one unforgettable photograph. But Starfish Prime teaches that the quieter half may matter more, because the hidden aftermath can be larger than the blast, broader than the witnesses, and longer lived than the people who planned it. It is a story about how the universe can take our violence, bend it through invisible rules, and give it back in a form we never meant to create. So if you ever hear someone say, "Space is empty, calm, or too far away to matter to ordinary life," remember the red sky over Hawaii. Remember the streetlights blinking out. Remember the satellites dying inside a belt of man-made radiation. And remember that one night in 1962 taught humanity a lesson it had no safe right to learn that way. Before you go, subscribe and turn on notifications if you want more true space stories where the facts are already strange enough without exaggeration. Then tell me in the comments which part stays with you most: the glowing sky, the invisible belt, or the idea that Earth itself helped hold the damage in place. And if this story changed the way you think about space, share it with someone who still sees the sky as empty. Thank you for watching, and thank you for being here.